Alright, so I'm going to be explaining this circuit. The previous video was me just building it, but I'll just be explaining just where everything is and just briefly go over how this correlates to this, and then after that we'll answer some of the questions. And a PDF of this will be submitted in the Blackboard link, so all the answers that I have will just be there, easy to see. So but yeah, let's get started. So let's start off with our 15-volt source. That's going to be right there, and let's zoom in so we can see where that correlates to this. So as you can see, it's right there, and that's going to be the second one down. So this row, so it's going to be this one. So right there, row number 5, right there, that correlates to this. So that is that. So now we need to find our resistors. So our 6.8K resistor is going to go into the collector of the transistor, which our transistor is right there. Our collector is the top one, base is the middle one, and our emitter is the bottom one. And so let's see. Our 6.8K needs to go into the collector. Well, it's not this one because, yeah, it's not going to be this one. That's the 56K, since the 56K goes into the base. So we found this one, since it starts off there, and then goes into the base, which is right there. So this resistor is our 56K resistor. So that means this is our 6.8K resistor. So it goes down from the 15-volt source into there. And you might be asking, oh, well, that's not the collector node of the transistor. That's all the way down there. But actually, this yellow wire right here is connected to the same row as our collector, so it goes all the way up to row 11, which also happens to be where this is connected, our 6.8K resistor. So our 6.8K resistor goes down from the 15-volt source into row 11, and then this yellow wire connects row 11 to the same row that the collector is on the transistor. So we now know that our 6.8K resistor is connected to the transistor properly according to the schematic. Alright, so we've got this, and this pretty much checked off to be correct. So now let's find these two. Let's do these two. So we know they're both connected to the base, which we know is going to be the middle one, which is, we know they're going to both be connected to the base, which is our middle one. And let's see, so right off the bat, we can see that we've got our 1 microfarad capacitor correctly connected. And the polarity is correct because we have the longer end right here in the base of the transistor. And then we have our shorter one, our negative one, going into our VN, which also comes from this right here. This wire is our VN. That's the analog output 0 from our function generator. It's going to be going into there. So that does check off our VN. We got that correct. So we got our VN, and then our capacitor on the short leg going into there. So we got our VN on this right here, and we got our capacitor with the short side, the negative side, connected to the VN. So that's right. And then the longer side goes to the base of the transistor, which that is how it is. So we got the capacitor, the 1 microfarad capacitor checked off. Yep. So let's find our 4.7K resistor. That also has to be connected to the base of the transistor. So let's find that. It's not connected there, but it's not connected to the same row as our 1 microfarad capacitor, but it still is connected to the same node because of this green wire right there. The green wire makes row 19 and 20 both equal to one giant node. So, as you can see, it's going in from the same node as the base on the transistor into ground, which is consistent with the schematic, so we know that's right. And, alright, well, let's see if this one's right. So, this 470 ohm resistor, let's see if that's right. So, as we can see from the schematic, it's coming out of the emitter of our transistor. So, we've got our emitter right here, and it's connected down into this row with this brown wire. And here we have our 470 ohm resistor going into ground. So we know that because of this brown wire, that we've got a connection from ground to the emitter with a 470 ohm resistor. So we know that is good. Finally, that leaves us with a 0.1 microfarad capacitor and our load resistor. So we can see that our 0.1 microfarad capacitor is connected to the collector node of the transistor. So let's zoom in and find that. We've got our collector right here at row 19. And it's not connected to anything directly because it's everything that we're using to connect it to is with the yellow wire. So we're going to go up. So we start off here at the collector. We go up to row 11, which is where everything that is connected to the collector node of the transistor is. So right here we still have our 6.8K ohm resistor that we previously discussed from the top, from the 15 volts DC. And then in that same node, we have our 0.1 microfarad capacitor, which is coming out into row 11 right there. And then, let's see real quick. So, yeah, we're here at the collector. Go up to row 11, which is still touching the collector because the yellow wire connects it. And then we go to our 0.1 microfarad capacitor we connect one node of the 0.1 microfarad capacitor into the collector of the transistor with one end, and then the other end goes into row 14, which we use to connect our load resistor here into ground. So both one end of this resistor and this end of the 0.1 microfarad capacitor are in row 14. And yeah, let's see if I can make it more visible. Yeah, you see that's in row 14, both this one and this one. So that is, this side of that resistor is that side. This side of the resistor is in there in row 14. And it's in there in row 14. And then that side of the capacitor is also in there in row 14 with the resistor. And then the other side of the capacitor, this side, is right there in row 11 with the yellow wire connecting it all the way down to our collector node of our transistor. So as you can see now, we completely have the circuit built. And now let's begin to answer some questions. If you wanted to see me building the circuit, you can refer to the video of me building the circuit. It's just that it took too long to... I just thought it would be better to have 2 separate videos. One me actually explaining it, and one just me building it just to prove that I did it. So anyway, construct the practical exam circuit wired to the plus 15 volt DC power. Connect VN to the MyJack function generator signal. Yep, we did that right now. Use the MyDAC or handheld DM voltmeter to measure the DC voltage across the 6.8 kilo ohm collector resistor. Record this value here and show your screen. Explain how to measure this current value and state what you measure. Alright, well, to do that, we're going to need to open up our digital multimeter, and we're going to need to have our probes connected into these two, because that's what you do when you're measuring voltage. So I'm just going to put the probes here across our 6.8 kilo ohm resistor, and I'm going to have them there. And then I'm going to take the camera and show that that's what it is measuring. Oh, we want it this one. Alright, so we've got our probes there across the 6.8 kilo ohm resistor, and hold on now. Got loose. Right there. 6.8 volts. Oh, yeah, it's a little loose because I'm not holding it, so I have to move my hand to aim the camera, but it is, you will get around 6.7 to 6.8 volts DC. So that's what I have there. So that is what I have there for number 2. Let's just try and do that again, just to get it for longer. So it's only for a brief amount of time that it was showing. Let's just get that in there. Okay, yeah. Got loose. Just want to show our schematic alongside. So right there, wait a minute, hold up. Guess I'll have to hold it a little bit. So right there we have our resistor, our 6.8 kilo ohm resistor that we are measuring. We put the black one at the bottom, since that is, yeah, so the voltage comes out right. And as you can see, you get, here, let me hold it harder. You get 6.8 volts around that when you hold it like that. You have it better. All right. So we know that we have 6 6.8 volts across this resistor with how it's currently set up. So, okay, now let's move on to the third question, which is, use the MIDAC or handheld DM meter to measure the DC current across the 6.8 ohm collector resistor. Record this value here and show your screen. Explain how to measure this current value and state what you measured. Alright, so to do that, we're going to have to change our settings on it to be measuring current, and here it changed. Before, we had to connect it to the high and common on that way. Now we have to readjust our probes. Oh, and also we need to change this to be within range so our multimeter can pick it up. 20 milliamp range will be sufficient. Alright, so we need to remove this one, put it here, and okay. Now, also, when you're measuring current with these, you can't just put it across simply like you would when you're measuring voltage. You have to, here, let me zoom in. So we want to measure the current going from here to here. To do that, we're going to have to disconnect this, put it somewhere, and then we're going to have to go into series with the probes, and remember though, we're measuring the current going from here to here. So we're going to disconnect that, and then put our amp meter from there to there. So we're going to need to put one end of the probe on this side of the resistor and the other end into the collector node, which was row 11 with the yellow wire. Or you could just put it directly into the collector node down there. Both will give you the same thing, and I will show that, as they are both, after all, one node. Alright, so let's do it. Let's put one right there, and just try and get this to be in a way such that it can stay by itself, and then I can move and show you how it's doing. Okay, so we got one probe. Just want to get it nice and tight. Yes, like that. And then I could put the other. Let's try and get the other in there. Have to be careful not to short it. Can't touch multiple wires at once. That would be bad. Yep, we're getting around 1.02 milliamps. We do this. It is not going to be easy. Okay, let me put this. Stand this up. We got there. Okay, I'm gonna just be off here I'm gonna be here measuring it off camera because there you go. You get 1.02 milliamps when you do it like that. So what we're doing is this. Putting one probe here, and then another here into the collector. Like that. And that is what gives us 1.02 milliamps. And remember, let's show it. So yeah, what we're doing is we're putting it like this. You can also go straight into row 11. Row 11 is the same as row 18 there. But why? Because they're both connected by the yellow wire. So if we do this, it will give us the same 1.02 milliamps, and it does. Okay, so that is part 3. We got 1.02 milliamps DC. And let's see what the other one is. Set up the function generator to a 5 kilohertz sine wave and run it. Use your 2 scope channels to observe both V in and V out. Remove the load resistor, R load, since you will begin with an unloaded voltage measurement. Adjust the function generator amplitude so that the output is not clipping. Set up peak-to-peak voltage measurements for the 2 scope channels. Record the 2 V peak-to-peak measurements here and show your screen. State what you measured. Alright, so we're going to need to generate that signal into RVN. And I will just be here and pull that up. So, nope, don't need that yet. Here, so it's a 5 kilohertz signal. And let's leave it as 5 kilohertz, and let's leave it as 1 volt speed. It's a sine wave. So what is happening is we're generating that signal from analog output 0 into here, which then goes in through that side of the capacitor into the circuit, just as you would expect. It comes in from that side of the capacitor into the circuit. And oh yeah, now we need to set up our probes. So let's zoom in. Right here, analog input 0. Well, the negative sides of our analog inputs, and I guess our output, they're all connected to ground, obviously. And to measure our output, we're going to take the 0 plus and go into our input, which is this row. It's this whole row right here. So it is the same row as that right there. So let's get our oscilloscope and see that. Let's enable, let's run it. Just adjust it to be nice and decent looking. Nope. Yeah, that's decent. So we've generated our 5 kilohertz signal with 1 volt peak-to-peak voltage. Yep. So now we need to measure our, let's get back to the question. It's asking to begin with an unloaded voltage measurement. All right, so that means is we're going to remove this and then measure the voltage here. So let's do that. So this is our, oh yeah, and we better connect this to be back where it was before. Yep, because we disconnected it for a bit to measure the current, but we better put that guy back in there. There we go. Just as it should be. Okay, now we need to disconnect our load resistor. And now we need to put our other probe. This is going to be the blue that represents our output. The green is our input. The blue is our output. And we need to put that on right here. Right there. Where we just put that, it's going to be right there. If we do that, let's see what output that gives us. And so we get a 13-volt output. Yep, around 13 volts is what we get. A 13-volt peak-to-peak signal for Vouts. Alright, let's move on. So that is our unloaded Vout peak-to-peak measurement. Our input measurement peak-to-peak. Our input measurement was 1. Output was 13. And just show again one more quick time. Our green is just 1, and our blue is 13, which is consistent. Alright, so let's move on. Now add the load resistor since you will be making a loaded voltage measurement. Alright, let's do that. So we're just going to simply connect him back into it and do it and see how that changed. And there it is, 5.9 volts. So 5.9 volts is what we get for there. So our unloaded voltage gain is just going to be our V unloaded out divided by our input. So 13 divided by 1, 13. So we get 13 there. And our loaded voltage gain is just going to be our V out loaded divided by our input, which is 5.9 divided by 1, which is 5.9. 5.9, yeah. So those are our two gains. Use the unloaded and loaded output voltages to calculate the output impediments are out. So I have right here, let me just so we know that our VS is going to be, that's going to be equal to our unloaded, because when we measured it to be, when we took the unloaded voltage, we got 13 because it's unloaded. VS 13, since the voltage here is the same as the voltage there because no current's flowing. So using that, when we redraw it in this way, we know that VS is 13, and when we took our loaded measurement, we got 5.9 there. And we know that's 6.8. We're calculating for that. So when we do 5.9 volts is equal to the voltage there, which is 13 times just a voltage divider, 6.8 all over 6.8 plus RS in kilo ohms. And when you solve for R out, you get 8.81 kilo ohms. And yeah, and just a few more final remarks is that the gain we calculated is pretty consistent with what was discussed in Lab 7, because, let me just pull that out now so we can still see that. This lab. Because at the end of the day we have an input AC signal going into there. Here, let me just compare it just to show you how similar it is. This is just something I kind of noticed. So yeah, we got an input AC signal there, DC power supply. Well, right here we got an input AC signal, DC power supply there. And yeah, I got a resistor there, got a resistor there, got a resistor there, we got a resistor there, resistor there, resistor there, capacitor, capacitor there, resistor there, resistor there, and then we got our RE, big RE, and our little internal RE. We got our big RE there, and our little internal RE there. And when you use the gain formulas from that lab, here, it's going to be AV is equal to negative RC in parallel with RL all over RE plus RE. And our RC is this, and our RL is this, and our RE is this. Our little RE we have to calculate. That's just going to be equal to 26 millivolts all over the current, the DC current going through the collector. And when you do all of this, I mean, the RE is going to be tiny. Even like if you do solve for it, it's going to be around, I don't know, maybe 20 ohms maybe. But anyway, when you plug in all these numbers, when you plug in that for RC, that for RL, 470 for RE, and just when you calculate that, probably right there and put it in there, you're going to get around, let's see, you're going to get around 6.18, I think, which is pretty similar to this. And it is the same kind of circuit. It's an amplifier circuit. And also, so that was for the loaded. When you do the unloaded and just do pretty much the same thing, but to have it just be RC, you actually get 13.6, I think, which is very close to what we got again. So there is a consistency in the theoretical formulas from Lab 7, this circuit. Yeah, that was all. Thank you.